I don't know how many, but I tried to do it. But after I did actually forward.
Oh yeah, we can do that. Like you said,
Looking at the notes.
okay.
Basically, like,
I'll mention, like I didn't quite get to this last time when we actually pushed so for the instruments, you're not going to be able to ask this exact property that the property has exactly in front of me. So you have to relax. Everything still essentially works.
right, so this could
So this is typically how it's written.
So this basically just saying like you pick a random pair, like some like delta between these, like you're just trying to fit it in. Like, what is this?
So I'll draw a picture next lecture. If you remember, we had this line going out when the probability and the similarity is equal to probability. Right? What you want to get is a separation. It looks kind of like your nest. You want to get probabilities above something. It's above a threshold and something is below a threshold. And I don't really, the area between, I don't really have any areas. So I'm going to say, starting, all I care about is that something is above the threshold, below something. Quadrants. And then I can separate those quadrants. And I'll draw a picture explaining this.
So like, it should be relative to like
it depends on that, but only like it's only going to put that inside some logarithmic that turns out that's actually kind of a signal. It should be safe or something.
I thought about
You don't need to use it. If you're building your own hash function, make sure you set all the otherwise you might get some of the weird errors. So let's get started. So welcome back, everyone. Welcome back, almost everyone, I guess. Not quite as much attendance as we're having. Hopefully, everyone else is joining in online. The people who probably need to hear this are the people who aren't. But there's, I encourage you to try and come to every lecture, or at least watch every lecture so soon after during the class. This is for two reasons. One, the students who do this tend to do much better in the class than the students who don't. So if you can manage to do this, it will help you in the class. Two, kind of, there's like part of this class where, I'm testing you on some core material that is being covered. And then there's a whole bunch of other stuff I'm hoping you learn that is harder to test on, partially because it's more kind of this kind of less quantitative stuff, and I think just good things to be exposed to. And another, because we're not as sure how to test on it. We're actually there's some research proposal going tomorrow about how to test on some of these things, but it's another story. The other reason is that this class has a very diverse starting point of the students, and so I'm trying to kind of make stuff interesting for everyone in the class, and sometimes that means we're going to go and see some cool stuff beyond what you would what the core stuff that I'm going to actually test you on. And I hope it's really cool, interesting stuff. But if you don't come, you're going to totally miss out on this. So let's look at the schedule quickly. So we just went through this 3 sequence of lectures, which are kind of like so in some ways like the whole class in a nutshell, in that we talked about some explicit modeling of some raw data in those challenges. We talked about some ways of representing this, which use some randomized algorithms and kind of maps it to a space a way of thinking about that you're not that you're not necessarily used to. And then we talked about some algorithmic challenges for scaling this up to very large sizes, right? And so this was both kind of, and then there's the trade-off in between doing all these things. How do you put all these things together? And in some ways, this was not, I think these are interesting techniques in themselves, and they generalize to other areas, but they're also not kind of the completely most core things that we'll talk about. When we talk about clustering next, we'll be talking about some very kind of explicit core things, techniques you should all know are going to come up for almost everyone in this class, where this might be a little bit more specialized. But the techniques we're covering in here are going to kind of versions of them, and the ideas we're talking about are going to show up in a lot of the rest of the semester. This is going to include the lecture today, which is just on the idea of like distance. Okay, and it might seem weird to just have an entire lecture just on the ideas of distances. There are going to be no algorithms in the, I don't think any algorithms in the lecture today. It's going to be more talking about the trade-off between mathematical properties and the modeling you'll have to do. But these kind of differences and kind of different definitions we'll see today are going to show up in important concepts later on in the class. They're going to be kind of very important later on, starting in the cluster. But also in like the dimensional reduction and regression issues as well. Okay, and then let me just mention again, there was some stuff in the LSH lecture on doing LSH with Euclidean distance, which I only just previewed at the end. We're going to I'm going to squeeze that into the lecture on Wednesday. This one's going to be pretty full, so I won't have time to do that, but we'll discuss these issues here. On Wednesday, also something fun on Wednesday. Part of the lecture will be technical about some kind of techniques about doing kind of nearest neighbor. So searches quickly. But another part we'll be talking about these very an instance of these very high dimensional vectors. And we're going to talk about some. We're going to talk about some explicit. So we're going to talk about some explicit sort of like ethical issues that are going to arise in this representation. So I previewed this a little bit I think in one of the lectures on the similarity, but we're going to be talking about these word vector embeddings, which are these representations of words in high dimensions, which are supposed to capture similarities between words. But there's some ethical issues in what other concepts are kind of maybe accidentally encoded in these representations. So this will be about 20 minutes of the class, but if you want to kind of really be, kind of get a preview of this, I would suggest you all to try and read the paper linked here. It's a pretty high-level paper, and what you need to know about these word vector embeddings kind of as a starting point, we kind of captured these kind of at that level already. I'll review them a little bit before we talk about this. But there'll be some kind of free discussion on this as well. So these will be kind of wrapping up loose ends on the stuff with kind of the issues with similarity, and then we'll start kind of using these kind of notions of similarities and distances as a block box within the clustering section, which will begin next week. Okay, and so this homework you should be so probably pretty close to done with, which is due Wednesday, and the LSH homework, you should definitely be able to do the first part of this. The second part, we will, I think, partially cover today, and then finish up some stuff that was moved to the lecture on Wednesday. But if you look in the notes, you can figure out the little pieces I'm asking to do. So if you want to get a head start on that, I don't think you're too far off. Okay, any questions on the schedule? Yeah.
When will we get feedback on our proposals?
Yeah, so we're still working through those. So this week, so Benway is the TA who's supposed to pre-process these. He's covered. There's a TA sick and traveling, and he's covering all the office hours, so it's a little bit slower than normal. They'll try and get all the feedback back by the end of the week, but I encourage you to come and talk to me as well. I'm not going to give direct feedback on most of them, because most of them are probably just, this looks good so far. If you want more feedback, you should come and talk to me after class. It's a great time. Yeah. And I will make sure to give explicit feedback to all the proposals, projects, but later on in the semester. Okay, great. And crash again. Okay. All right, so we're going to talk about distances, and so in case you have not thought about a distance as like a mathematical object before, it's going to be a bivariate. So function. So we'll say d. It's that. So that's going to go from from some domain across this domain. It's taking in two elements, and it's going to the real numbers. And in most cases, these real numbers are always going to never be negative. So I'll write a plus up here. Sometimes instead I'll say so it's greater or equal than 0. Okay, so in this lecture, I'll say something like d of a and b, is then going to equal a value, right? And so this will be a real value that we can kind of, it's important that it's real, so that we can compare and say one is smaller than the other, right? And so 0 is it is going to be as small as possible. So this does not say a lot about what about what a distance is, and there can be a lot of functions which are distances, and a lot of them are reasonable. And today's lecture is going to be kind of list some properties of them, and then talk about kind of some examples which are coming up very frequently in so inside data analysis, and these will, so I'll try and give kind of tell the story of when one is useful and when the other is useful. So, but there's this important property that's called a metric, which you often strive to have for a distance. Okay, not all distances count as metrics. We'll see some which are not metrics, but this is like a special property of a distance, and so it has like 4. So in order for a distance to be metric, there has to be 4 things which are satisfied. So I have to say that d of a b is going to be greater or equal than 0. It's often called non-negative. So kind of if it actually goes to r plus, then this is going to satisfy this. All right. So m2, then d of a and b are equal to 0 if and only if a is exactly equal to b. So the value is only 0 if the two objects are exactly the same. Okay. So this is often called the identity. So, and the first two are sometimes grouped together in one property. But you can often, sometimes we'll have M1 without M2. Okay. D of, and then the third property is that D of AB is equal to D of BA. So this would be, so like this would be symmetry, right? So if I'm going from A to B, it's the same to go, so back to B to A. So one way of one way of measuring distance is like the amount of travel time in between one place and another. So if I look at my distance from my home to my work, it's a reasonable distance, but it probably does not satisfy this property. If I have to make more turns which are going left on the way into work, those probably take longer. The actual driving distance might actually be slightly longer too, right? If I'm restricted to drive on certain roads, and the roads have a one-way structure to them, then this is not going to necessarily be satisfied. But it's still a useful distance I might want to use to, in order to model some places on the map. Okay. And then the fourth quantity, and sometimes when they say metric, they only refer to this quantity, is that distance between any A and B is going to be less than or equal to the distance from A to some C plus the distance from C to B. And this is known as the triangle inequality. Okay? And so this is kind of, so this property is fairly intuitive. It means if I'm going from A to B, right, and I'm measuring the distance somehow going from A to B, that if there's a third point up here, C, and I could go from A to C and then from C down to B, that it's never faster to go through C. Okay, this intuitively makes sense because if I could, then I would actually define the distance from A to B possibly as going through C. If I could do that route, then maybe I would define that as the distance. So it's always shorter to go straight instead of having to go through a third point. Now these could be equal if C happens to be on this line. Okay? And so, whether it's actually a line, I kind of intentionally did not draw them as straight lines here. Although this will be true if you are drawing the straight line distance. Right. Okay. So and there are some distances we'll talk about some in the lecture today, which are used heavily in modeling data. but don't necessarily satisfy this property. Okay, but they come up because they actually, there's some information theoretic or some probabilistic notion that makes sense to think of, and then you can write it down as this distance. That's the right kind of derivation of what's going on, but it does not satisfy this triangle. And then what we'll use this for, in some algorithms, they'll work for any distance which is a metric, which means for these kind of formulations, I can't have any guarantees about those algorithms. Okay, so we'll see algorithms later in the semester that will work for any distance which satisfies these properties. Okay, and as I'll mention, being locality sensitive, there being a locality sensitive hash function for a distance, if it's like set based, then it's related to 1 minus the corresponding similarity. So being a metric. Okay, if that is a metric, then it usually kind of that's pretty close to being the requirement for it to have some sort of locality sensitive hash being available. Where if the ones that are not a metric, there's often some issues. Okay, there's something more formal that can be said, but it's not. But that's the main point. Okay, so if they're kind of subsets of these which sometimes come up. So okay, so if I have my pen, okay, M1, if I have M1, M2, sorry, if I have, let's see, M1, M3, and M4, then I would call this a pseudo metric. Okay, so this is kind of like a metric, but I don't have that two things are only equal to 0 if they're exactly the same. So there's a very common one used to model like these bag of word representations from text, which is going to be only going to be a pseudometric. It's not going to have this M2 property. But we'll explain why this still makes sense. And this removal of this property is actually on purpose. I want things to be 0 even if the data is not exactly the same. Okay, and then if I charged my pen, but it's not writing. Okay, if I have M1, M2, and M4, okay, then this is going to be called a quasi-metric. Okay, so this is not going to have the property of like the symmetry, but it still has the triangle inequality. Okay, so it could be that the driving time distance that I described might satisfy this. It might only be 0 if I'm starting and stopping at the same place. They're always positive. It may satisfy the triangle inequality. It probably does, because if there was a shorter route, I would take it. But I might not have it that it's symmetry. Going from work to home is not the same as home to work. Okay? Okay, so you can have these different things, but these are kind of basically almost one of the only general mathematical rules about what you want so like inside the distance, if you don't know anything else. Yeah.
So did you say that if distance satisfies all the rules, then you can take Descartes similarity as 1 minus the distance? Or not, just for similarities?
So there's like a family of distances which are typically based on sets, where this domain script X, right, A and B are sets, where you take a similarity and a distance is 1 minus that similarity. And the common example is Descartes, but I listed like 5 other ones. Okay? If that 1 minus the similarity, I use that as a distance, if it satisfies a metric, then, there are some other technical ways of how I could write it, but pretty much that's the main thing, then there is some LSH function. there is a way to define a locality-sensitive hash function, which will allow me to quickly retrieve all the things that are within some similarity. They're not quite as simple as min hashing, but there are ways to do it. Yeah, so that's one of the implications of being a metric. We'll see other ones as well. Yep.
In terms of like data mining, how does asymmetry come into picture? Because does it make sense to say that A is similar to B, but it's not the same as the distance between B and B?
So I mean, it could be, for instance, like I think the best example is like the driving time distance. I can start with a bunch of points on the map, and I can use the API of Google Maps to say what is the driving time distance from one point A to B. And then I can try and understand how to cluster these points, for instance, just using this distance, right? And I could use that instead of the straight line distance, which we'll start talking about next, right? Now might be a better way of modeling the closeness between places, especially in a city with complicated driving directions, trying to get across a freeway, from one freeway to the next. If I'm trying to if I'm playing for vacation and I'm trying to book a hotel and I want the hotel to be close to the beach, right? I don't necessarily care about the straight line distance. I care about how long it takes to get to the beach and how long it takes to get back. And so this might be the right way to measure that, but that's not necessarily a straight line distance, right? And so that's the right modeling tool to use, but it unfortunately may not satisfy these properties. And so we should be aware that then if I run an algorithm, I could probably run the algorithm and hopefully it terminates, but I won't necessarily know if the algorithm actually worked like it was supposed to. Right, and so we'll see some examples of that later in the semester, in just next week. But things so like the straight line distance, the L2, the Euclidean distance, the next slide I'll talk about that, satisfies this, but also things like the Jacquard distance, right? So it's a pretty broad abstraction, it turns out. It doesn't satisfy everything, right? But it kind of covers it can be a distance between any sort of class of objects that you can think of it in these properties. Okay. So I next want to specify. Oh boy. Okay, I'm going to try and restart this program. Hopefully, Pencil becomes more awake. Okay, so let's see. I want to talk about LP distances, and so these are defined where this class of objects is going to be right. Try something else. So the class of objects I'm talking about is going to be RD. So it's going to be the space of d-dimensional vectors. Okay. So that means that A and B are going to. I'll say that they're in RD, and that means that A I can write as this vector A1, A2. Up to AD. Okay, so I've got D coordinates. Each coordinate is going to be a real value. Okay, we'll talk. This representation comes up all the time. It's okay if they're integers or other things as well, but we'll talk more on the lecture on Wednesday about different scenarios where this comes up. If you haven't seen this before, this is kind of you typically want to map your data into this representation because most algorithms that are come up in data mining machine learning would like to use this sort of representation for your data. Okay, so now so if we're looking at this, we often think of distance, the most common distance. Okay. I think I figured what the problem was. Okay, good. So is the L2 version of this? We'll write this as L2 of A and B, or D2 of A and B, or we can write this as the vector norm of this difference between A and B. And in fact, this vector norm is such a popular vector norm, then if we just write a vector norm without any subscript, that's referring to this distance. Okay, and so this is defined as the sum over the coordinates 1 to D of AI minus BI squared, and I take this whole square root. Okay, and this is the case now where A and B are these, think of them as points, and then this distance is the straight line distance in between them. D2, A, and B is the distance of the straight line. Okay, and in here, in this representation, I can think of them as having two coordinates, an x and a y coordinate. So this A equals AX, AY, right, where this is the x and the y coordinate, and this same with B, this is BX and BY. But this works in even higher dimensions. Still, the straight line distance is defined in this way. Okay, so hopefully everyone's seen the Euclidean distance before, but I wanted to write it up because it's really important. Okay, so this satisfies the triangle inequality. So okay, it has to be greater or equal than 0. It's going to be symmetric because the roll inside the subtraction, I'm squaring it. Right, so it doesn't matter if it's A minus B or B minus A, because I squared that gets rid of the sign. So it's symmetric. They can only be 0 if every single coordinate is exactly the same. Okay, and the triangle inequality I can satisfy by basically drawing a picture of a triangle, and I can't get from A to B in a shorter straight line distance unless I go on the straight line. Okay, so there's a proof in the textbook if you want to see it, but that's the kind of, it satisfies the metric property.
So the LP distance is only where your domain is numbers or coordinates.
Yes, so LP distances are defined over vectors of like a fixed length, right? So I know the length of the vector. Yeah. Okay, good. Okay, but this is not the only, this is sometimes called the Euclidean, so distance as well. This is in reference to non-Euclidean distances where I'm not on a flat surface, but I'm like on the surface of the Earth and it curves. We're not, actually we'll talk about this a little bit, or it can curve up like a bowl and other stuff. But so sometimes called the Euclidean distance. This is not the only LP distance. The L1 distance between A and B, D1, A, B, I would say A, B, 1, right? So this is defined as instead I equals 1 to D of AI minus BI. Okay? This is simpler. I'm just taking the sum of the absolute values. Okay? And for this distance, it helps to actually have the grid on the paper here. So if I have A and B, then the L1 distance is any distance that goes on this grid. Okay, so I have to walk on the grid. It's the length of the line on the grid. Okay, it's and you know it doesn't matter what the path is. It's equivalent to if I go here. This is the green line and the blue line. These are the same total length. Okay, so any walk on the grid that does not go past, you know, if I go down here and then back up, that's going to take longer, right? But any kind of shortest path on this grid. So I'm walking first in the x coordinate, then in the y coordinate, for instance, right? That's one way of doing it. So that this is sometimes called the Manhattan so distance, because if you're in Manhattan, except for kind of some streets, it's mainly laid out on a grid. You know, there are more of these weird cross streets so if you're in like Manhattan, then if you're in like downtown Salt Lake City, so let's, you know, we can call this the Salt Lake City distance. If you're walking on the actual blocks of the city, or you're driving downtown, you have to drive on the blocks in the city. You cannot fly like a bird in between them. Even the bird might run into buildings. So you have to kind of walk on this, drive on the streets. And so that's the distance you have to travel. Okay? So sometimes this is better for modeling, again, for these kind of traffic situations, for instance. This, you might want to use this. And it's going to have different properties. It's going to give you different kind of distances, and you might change the order of which pair is closer. And I'll kind of show you a way of thinking about that soon. Okay, but it also satisfies all these properties of the metric. The symmetry and zero properties satisfy just by definition, and the triangle inequality, you can argue kind of intuitively, you can see that being forced to go through a third point can only make it further. It can't make it any shorter. Okay. Let me just write in general now the LP distance between A and B, A minus B, with the norm being P. This is defined as I equals 1 up to D of AI minus BI to the power P. Then I take all this to power, so all of the whole point to the power 1 minus P. Okay? So if I notice if I plug in 2, then the power 1 minus P is power 1/2, which is the square root. Right? So I recovered the L2 distance. If it's a 1, then the P and the 1 minus P aren't there at all. Right? So I recover the L1 the L1 distance as well. Okay. So it turns out every LP distance for P in from 1 up to infinity is a metric. Okay, I can choose any value P between 1 and infinity, and this is a valid metric. Okay, so 2 and 1 kind of made some intuitive sense. I could think of instances where I'd want to use those. 2 is generally the most common, but 1, there are definitely reasons why I don't want to do this. But anything for any value of P between 1 and infinity is valid as a metric as well. So I could do P equals 3. That's perfectly reasonable. I could do P equals, so I could do something like 1.5. You know, it's not common to do these things, but these are valid distances. And they satisfy this really powerful property, a metric, right? So how do you choose which one to use, right? If you can do LP, if you can't do L2, typically do L2. That's the short answer. But we'll see instances where you definitely want to use L1 instead, okay, in the class. I'll mention a couple of other. L0 is well, this has a special definition. So I'll write this as D minus 1 to D of the so of like the indicator function of A AI is equal to BI. And so if A and B are if these are in 0, 1 to the power D, so these are bit strings, then this is the then this is a Hamming distance, right? It's the number of bits which are different in between these strings. But I could define this if they're real values as well. So it's just the number of things which are exactly the same. The number of items which are exactly the same. Okay, and then the L infinity distance is also comes up. Okay, defined this way, and this is basically equal to the limit as p goes to infinity of the LP distance. Okay, so I start with the LP distance. I say, I said this was a metric up to infinity. It's not defined. I can't define 1 over infinity, right? So it turns out I'm going to give a special definition of this, and this one will also be a metric. And if I take the limit, what turns out is actually the if I just take the max of AI BI, right, the absolute value between the coordinates, I find the maximum difference between any pair of coordinates. So what's happening here is I'm taking all the differences, raising them to some really big power, and then I add them up, right, and then I take them to the 1 over that power. And so any small difference where one coordinate is a little bit bigger than the other, when I raise it to a big power, that's really amplified. Right? So anything slightly less than the max is not going to show up here. But the p and the 1 over p are going to kind of cancel out with that one term. Okay, so usually we define the L infinity distance as the maximum difference between any two coordinates. Okay, so this distance also is also going to make sense. Okay, and I just want to find which, I care about kind of this worst case, this L infinity case of the worst possible violation between all the coordinates I'm keeping track of. And this also comes up in modeling fairly often. Okay. Okay, so what's been fun to do that. Okay, I showed you the picture already. Okay, so if we look at all these LP distances, there's this kind of nice way of thinking about them as if I have one object, let's call this this object here. This is 0, but I think of this as B, and I'm taking the distance to any point A, and I want that distance to be 1. Okay, I want to look at the space of all the points which are distance 1 from B, and for the L2 distance, this is exactly a ball, or it's a in the plane so it's a circle. In higher dimensions, it's a sphere, right? All the points exactly at distance 1 for the L2 distance is this circle here. Okay. For the L1 distance, it's going to be this. It's going to be this diamond. Okay. If I add up, because I'm adding up this coordinate plus this coordinate here, right? For the L1, I'm going here, and then I'm going down to here. So I'm adding up these two distances, and when they equal to 1, it's going to be exactly on this line. As I slide this over, well, then I have to go down less, and I have to go up the same amount. So it's symmetric about the axes. And the only place they're equal is exactly when I have all but one of the coordinates to be 0. Right? So if I just have the x coordinate to be 1 and the y coordinate to be 0, well then the sum of the distances, or kind of the sum of the squares, or the max of the distances are all going to be the same. Right? And so the L infinity ball is going to be this red one here. It's the max of the distances. Here, the x coordinate is the distance 1, but the y coordinate is less than that. Right? So it doesn't matter. Only the coordinate, which is kind of the biggest deviation, is controlling it. Yep.
You mentioned a little earlier back about the distance around the world, like, because it's not really exactly like if you're to use the LT distance, so it would go right straight through the ground into to the other side. How would you which LP distance would you use to map around the curve of the curvature of the Earth?
So if you're doing that in curvature of the Earth, what you're going to use is the closest thing is going to be like is going to be like the angular distance. Now that's gonna be the distance on a sphere, not on the Earth. If you're measuring on an Earth, then you're just you're somehow measuring the shortest path on the Earth. And there are studies of taking these models of the terrain and then figuring out the shortest path, and how do you do that from a terrain model. Turns out it can be a challenging kind of algorithmic problem to actually just compute the distance between the shortest distance between 2 points while staying on a terrain. But people have studied this problem in detail. There's not a simple closed form solution where I just look at the coordinates and know it unless I assume it's a sphere. And if I assume it's a sphere, and then you can basically scale it, and you can look at kind of essentially the angle between the two vectors, and we'll see this. And that'll involve like the dot product. But we'll get to that in about 15 minutes. Yeah, but which is yeah. So all right. So okay. So looking at this picture, where would what do you think the L3 ball would look like? If I drew an L3 ball, where would this look like? Yep.
Just somewhere like a little bit like wider than the blue line or purple line, whatever that is.
Yes, it's going to go between the blue and the red line, between the L2 and the L infinity, right? So the L3 will do something like this. It's going to start going out into the corners, right? It has to meet at the axes. Has to meet at these axis points here. But it's going to be sandwiched between the L2 and the L infinity. So it's kind of reaching out into here. Because I'm cubing things, it's better to have more things which are in a mid-range than one thing which is more extreme compared to L2. Right? And if I did an L, so if I did like an L of 1.5, an L of 1.5, it's going to go inside of here. It's going to go, this would be a L 1.5, right? What's going to happen if, this is L3. Okay, what's going to happen if I do an L of, let's draw some black, L of 0.5. What would this L of 0.5 look like? Yep.
Would it be concave inside of this?
Yeah, so it's concave. And so this is actually, this one causes some problems. This would be L of 0.5. So if you see this, it's concave, which means, if you haven't heard of convex concave yet, it means that if I took the straight line in between any 2 points inside the ball, I should be able to, that should never go outside of this shape. Right? That would mean for a shape to be concave. So the L1, any straight line in between 2 points is going to stay inside, but for the L 0.5, that's not true. If I took these 2 points here, which are both individually have an L 0.5 norm of less than 1, but if I took the straight line distance between them, I interpolated, I'm going to go outside of the shape. And so this causes problems that it's not a convex shape anymore, and this effectively is why you don't satisfy the triangle inequality with this anymore. You can think about this shape and then come up with an example where it does not satisfy the triangle inequality. Okay, this is one of my favorite pictures. Okay, so what's going on here with these LP distances? Not sure where I got this from, but so this is it's a great sign. You've probably seen something like this before. They've taken population, feet above sea level established, and they've added these up. Okay. If you're using an LP distance, you should make sure you're not doing this. Okay. This is going to give you something which is nonsense, right? Okay. So this is absolute. This is so this is absolute nonsense here, right? If you've done this inside of some sort of your analysis, where I've taken things of different units, measuring different things, and I've added them up, this quantity doesn't have any meaning, and I should not be using it in my analysis, right? It seems reasonable thing to say. This is like a really common mistake. If I have an LP distance where the different coordinates are measuring different things, like I have a city and I have a bunch of cities and I keep track of information about them, population, feet above sea level, the data was established, and I measure an LP, the L2 distance between them, the straight line distance in this coordinate space between them, I'm doing this. Okay, I'm taking the difference between the coordinates, the distance from some zero, right, effectively, and I'm adding those up. And this does not make any sense. Okay, so don't do this. Okay, it's all right. So I have this picture in mind. If you're using an LP distance, the rule is all the coordinates must have the same units. Okay, they should at least have the same units. Okay, probably more than that. They should all be measuring essentially different versions of the same quantity. Like I have a temperature. I have a weather station, and I'm measuring the temperature at 8 different times. That gives me an 8-dimensional vector. I compare 2 weather stations to each other. That would be a reasonable thing to do. But kind of listing information about a city and measuring the distance this way does not make sense. Okay, so you'll see examples with like listing people by their height and their weight, and then measuring Euclidean distance between them. If I change the unit on the height from feet to inches, it doesn't change the data, but it's completely changed what the distance is. And it changes the ordering of the distances, right? So if I change feet above sea level they had to list feet here, but they didn't list feet in these other places. If I change this to meters, it changes what the distance is, right?
So with the height and weight example, isn't there some way to like normalize or standardize all of the values so that they correspond to one thing?
Yeah, so there are a bunch of these ideas about normalizing these values, and you can try and do this, but these are kind of also are fairly arbitrary. Do I normalize them between 0 and 1? Do I normalize them so that their standard deviation is 1? What happens if I have an outlier data point in all my data sets? Or I get a new data point after I've done this? Then I have to change my normalization. I have to redo everything. Right? There's lots of kind of challenges with doing this. We will have a lecture in class where I talk about kind of learning these trying to figure out if I have this situation, what I should do. There's not a good simple answer for it. And in general, the first case is just trying to avoid kind of relying on some distance without thinking about what it's meaning. Okay. Okay. So I'll tell you now though the first step towards solving this. Okay. There's something called the Mulholland-Novus distance. Okay. And so this is defined again. A and B are going to be vectors in RD. Okay, in RD. And I'll call this dm between A and B. Okay, and so this will be A minus B transpose M a minus b, the square root. And m is some parameter of this distance. Okay, so m is going to be a matrix, a matrix which is d by d, real value d by d matrix. Okay, if m is a positive definite matrix, then this distance is going to be a metric. Okay, so if you don't haven't had linear algebra before, it's probably doesn't make any sense to you, but hopefully you've all had linear algebra. I'll explain this a little bit to give you some intuition of what's going on. Okay, but this is going to be a square matrix M, and it's basically going to be a scaling of the coordinates, okay, in some way. M is telling me I'm choosing how to scale the coordinates. Say I did have vectors that were population, feet above sea level, and the data was established. How should I scale those in order to have the right distance between them? Well, if I can control them, that's controlled by M. And if M is, there are different ways I can scale them, and if as long as M is going to be positive definite, it's still going to be a metric. Okay? If M equals I, right? So the identity matrix, then d of I between A and B is going to be the L2 distance. Okay, what is this doing? If I think about that, the identity matrix, basically it drops out. If I multiply something by a full rank identity matrix, then it doesn't do anything. And what is A minus B transpose A minus B doing? That's basically it's basically the squared distance in between those vectors. Okay, so A minus B transpose A minus B. This is the dot product between A minus B, A minus B, okay, which is the two norm between A minus B. Okay, so so if I put M in there, sometimes I write the M in this norm here. Okay, I sometimes write subscript the norm with an M is sometimes what the notation is. Okay, so if I have the identity matrix, that's basically saying I'm not scaling the coordinates at all. I get back just Euclidean. But if I do scale them, then it's interesting. If M is a diagonal matrix, let's call this M1, M2 up to MD, right? So then it looks like M1, M2, MD, and so all these are zeros. Then these values are just scaling the individual coordinates. M1 tells me how much to scale the first coordinate, M2 how much to scale the second coordinate, and so forth. So if I think the first one is twice as important as the second one, then I increase it, then I put M1 should be twice as big as M2, right? Okay, so as long as these are positive quantities, then it's going to be positive definite, and it's going to be a metric. But I can fill in these stuff off the diagonal, and we'll talk about this more after we've talked about and reviewed stuff like PCA, and that'll make a little bit more sense. But that allows me to skew it in other ways other than just scaling the individual coordinates.
So if it wasn't positive definite, but then we chose to just take the modulus of the complex numbers we got out of it, would it become a metric?
I don't know what would happen. Yeah, so I'm not sure what would happen. You don't want to just choose this M matrix arbitrarily. You want to choose it carefully and maybe use some knowledge about the data to choose it, and we'll actually see this later in the semester. So you won't choose it. So either you choose it so it's identity, so it's diagonal, or through some learning mechanism that we'll talk about.
So if go back to like the height and weight example, if we had we had a height and a weight, and let's say we had the height in feet, and then we changed the feet to inches. For the Mulholland Everest distance, would that encapsulate that?
If I change feet to instance, that's equivalent to like putting a 12, scaling one of these coordinates by 12, right? So it's still a valid distance, but why did I choose this one instead of the other one, right? If you can't justify that, then you're just doing stuff which you are not justifying, and you're just doing some black magic. It might work, it might not work, I don't know. Okay, but if you can't justify what you're doing, maybe you shouldn't be doing it. Okay, so there are certain data mining classes out there where they're just going to tell you a list of these techniques and say, look, if you have this problem, you can try using this technique. Here's where you run the software, and you'll learn to run it, but you might not know when and why it's working. I'm trying to kind of explain to you the situations where you do know what you're doing. Now, there's some cases where you're like, I don't know what to do still, and it's challenging, but I'm trying to tell you the cases where you can understand what is the right thing to do. Right?
Should M always be a diagonal matrix, or at least?
No, we'll see something later in the semester where we will learn an M, which is not going to be diagonal, but it will satisfy the positive definite matrix. It will be a sum of rank 1 matrices. Yeah.
Should it be a square or a b naught?
Oh, yes, thank you, Benel. Yeah, this is this should be square, because it's under the square root. Great. Good. All right. So yeah.
Using this distance, is it always under a square root, or does it?
Yeah. So think this is an analog extension of the L2 distance, so I need the square root. Otherwise, it won't satisfy the triangle inequality unless I have the square root.
Well, I guess what I mean is in the L2 distance, the power of the root changes depending on the dimension. Is that the same case?
No, in the LP distance, yeah, this is could be confusing. The LP distance, the power is depending on the P norm, but not the dimension. So P and D are different, right? So D and P are not. These are not the same thing.
Oh, okay.
Yeah, in statistics, they often use P as the dimension of the data. We use D because I come from computational geometry, where we use D for the distance. I think that's a little bit more common in machine learning as well, in data mining literature. Yeah, but these are not the same. P is for LP norm, and it's like L1 or L2 or L infinity. Okay, good. So let's move on to something slightly different. So we're still going to look at, we'll talk about so the cosine distance. And here A and B are still going to be in RD. Okay, and this is defined now as d cosine of A and B is written as 1 minus the inner product between A and B divided by the norm of A times the norm of B. Okay? And if, just in case you I haven't written out the definition of the inner product before, it's that. Okay, and these norms are the two norms, right? Yeah, so this is the cosine distance. So this is this going to be a metric? So can this? So the inner product is basically. Inner product from A and B is maximized if I keep the directions of the vector the same, if A is equal to B. And then it's equal to the squared norm. Okay, so this quantity this quantity is always less than or equal to 1. Okay? That's what this normalization is doing. It's forcing it to be between 0 and 1. So that means this term cannot be negative. Okay? And it's symmetric between A and B. Okay, so the first two properties hold. Yep.
Oh, we're going to ask a question.
Oh, well, I'm still asking, is this a metric?
No, because if they're equal to each other, they'll be 0.
Okay, but then the distance is 1, so that's okay. Yep.
If they're parallel.
Yeah, or if so an issue is going to be that, let's say this depends on the choice of the origin, and I've got A here and B is here, right? So I think of them in this way, and what the dot product is doing is it's if you remember what the dot product is projecting A and B. If B is a unit vector, it's telling that it's the length of the projection of A after if one is a unit vector. But if I importantly, because I'm dividing by the scale, so I'm effectively factoring out the scale of these data points. Okay, I'm removing the scale. So the distance between A and B, the cosine distance between this A and B is going to be 0, but A is not equal to B. Okay, so this is only measuring the direction. Only the direction. Okay, and so basically what I'm thinking of doing, so I do not satisfy this M3, this M2 property, that they're only 0 if the objects are exactly the same. What I'm doing is I'm mapping A to A prime, which is A divided by the 2 norm of A, right? And I'm mapping B to B prime, to B bar, which is equal to the normalized version of B. And so, so you can write this if I say instead that A and B are on S D minus 1. So this is the set of all points x and RD, so vectors in RD, such that the norm of x is equal to 1. Okay, so if I instead define my domain to be this SD minus 1, which is the D minus 1 dimensional sphere, which sits in D dimensions, right, then I'm going to satisfy the 0 property. Okay, I'm going to set, they're only going to be at distance 0 if they're the same, because I've basically taken all the vectors and I've normalized them. I've not changed their direction. Okay, so this cosine distance is the most common way to measure the distance between these. If I do some sort of bag of words representation of a piece of text, I have this long vector, 100,000 dimensional vector for every possible word, and I count how many times each word occurs. And I'm going to get different vectors based on, I increment the coordinate corresponding with each word. And what I want is that 2 documents are going to be similar to each other irrespective of their length. I've kind of normalized out the length. I'm just looking at effectively the distribution of the words. Okay, and so this only cares about the angle, just the content, but not the length of it. And so it's kind of factored this out through this normalization. Okay. Unfortunately, this is still not. This is still not a metric, even if I restricted the space. Okay, it doesn't quite satisfy the triangle inequality, and it has to do with issues of you can illustrate this. I'm now everything S1. This is S1. It's a sphere, and I can run into some issues where I have A, B, and C, or no, it's not the triangle. Yeah, no, maybe this is in. Anyways, there's some technical issues where it doesn't satisfy the triangle equality. So what people typically do is they, I'm not recalling them offhand, but they map to what's called the, so the angular distance. So if you want to kind of think about from a property, the cosine is often what people measure and report in papers, but the angular distance has a little bit nicer property. And the angular distance between A and B is going to be equal to the inverse of the cosine of AB, or the arc cosine of the inner product between A and B. Okay, so instead of doing a 1 minus something, I'm just taking the cosine. So I'm taking the inner product, and I'm basically inverting the inner product. This is assuming that A and B are in SD minus 1. So otherwise there'd be a normalization inside of here, which I've run out of room. But okay, but assume you've normalized your vectors, then this is the angular distance. Okay, and so the angular distance between A and B is exactly this length. If I go from the origin, I'm measuring this angle between A and B in, so like I'm writing down the radians of this angle. And that on a unit vector, for unit vectors, this is a unit circle, which is how I'm normalizing to, that's the arc length. And for a sphere in higher dimensions, that's the shortest path, the geodesic path on this sphere, is this angular distance. Okay, and so that's just the arc cosine of the inner product between A and B. This one turns out is going to be a metric. So this is a monotonic transform. So if I have distance between A and B and C and D, and I measure them in the cosine distance and the angular distance, they're going to have the same order. If one is smaller, they're still going to be smaller. I'm not changing the order. Whereas with like LP transformations between L1 and L2, that's not necessarily true. That's not a monotonic change in the distance. So this doesn't really change the ordering of which is the closest point, but it maps it into a metric. So the cosine is what's most commonly reported, but the angular is kind of the nicer version of the distance. So this one is going to be a metric. Yeah.
If this one's nicer, then why is the cosine used more frequently?
Well, I don't have to compute an arc cosine.
Okay.
An arc cosine is going to take a lot longer to compute, maybe a factor 10 longer, for instance, than doing the dot product usually. Just the way it's implemented. That could be the reason the cosine probably came up first, was simpler to think about. So the angular distance is kind of a little bit nicer, but the cosine is what's popularly used in the literature. Yeah?
So if we use the cosine distance to measure on a homework to measure the distance between our two vectors, would we see similar results, or is there a reason why we wouldn't do that?
Oh, in terms of, instead of, in the homework.
Yeah, homework.
Yeah, I mean, it's going to be like, so the cosine distance is going to, the other thing with the cosine distance, it can be, the cosine distance can be, it can be between 0 and 2, okay? Where the angular distance is going to be between 0 and pi. So it's a scale transformation as well. So you're going to be, the scale is going to be off, and then there's going to be some non-linear transformation of that scale. So, I mean, the ordering of which ones are going to be closer than other ones is going to be the same. but it's going to be in a different range. Sometimes this is divided by pi, so it's in 0 and 1. Okay, the other thing about the angular distance is that it has a cool, there's a cool, so locality sensitive hash. I'll just tell you this. Angular distance LSH. Okay, so I'm going to have everything is going to be, and let's just say this is d minus 1. I'm going to have 2 points A and B, where the angular distance is the length on the circle. If I'd drawn the circle properly the first time. Okay, so this is the angular distance in between them. A hash function. Okay, so I'm going to pick a random direction. So pick random unit vector u in u, and then I'm going to take the dot product with the unit vector. Okay, so if hash u of A is going to be the sign of A u. So I'm just going to take the dot product and look at the sign. So this one is going to be -1, and hash u of B is going to be +1. Okay, so the hash is just going to be a it's going to map to -1 +1. Okay, so it's a mapping into a domain of size 2, but this is an locality sensitive hash function for the angular between A and B, I think, divided by pi. So this is going to be the probability that h of u A equals h of u equals h of u B. Okay, so that's pretty cool, right? I just pick a random unit vector. I'm basically dividing the space in half. If it's on this side, it's a +1, this side's -1, and the probability that they're the same, it basically has to do with the probability that this line goes through the green region. If it doesn't go through the green region, then they're going to have the same sign, right? So if I have a different point over here, C, right? The length of this green region, this blue region, is going to be smaller, so the probability of splitting there is going to be smaller, so they're more likely going to have the same sign. Okay, so this was actually a precursor to the LSH for the Euclidean distance, which we'll do Wednesday, which will combine this idea and the gridding idea that we saw for the triangle similarity. Okay. All right. I want to quickly mention let's just mention one more distance. The KL divergence. Okay, so this is often written distance KL between A and B, but it's actually often not written comma B. It's A double bar B, and this is because it's not going to be symmetric. So this is going to be equal to I equals 1 to D of AI natural log of AI over BI. Okay, and so this is going to be for A and B in the space called triangle D, or actually defined it has to be positive. Okay, what is this space? So triangle D equals these points in RD with the property that the the L1 norm is equal to 1, not the L2 norm. The L1 norm is equal to 1, and then the triangle D plus, or maybe greater than 0 or something like that, is where it's such that the L1 norm is equal to 1, and for all I, xi is greater or equal than 0. It's greater than 0, yeah. So the first one has to be, yeah, so that's in here as well. This is also, and is greater or equal than 0. Okay, so what is this describing? I've taken a vector, when I've L1 normalized it, what is that representing? So L1 normalize it, I make it a unit vector, and I get kind of nice pictures that look like this. When I have this property, I can draw something like this as well, but the space of allowable objects now goes from here. This is 1, 0, this is 0, 1. And so it lies on here. It cannot be, they have to be positive, right? So it's in the positive orthant. And this forms like a D minus 1 dimensional simplex in higher dimensions is kind of like a triangle, then a tetrahedron, and so forth. We'll think about visualizing these a bit later in the semester. Okay, but what really is this? It's a probability distribution. Okay? If the sum of all the things, the L1 norm means the sum is equal to 1, and all the coordinates are greater or equal than 0. That's a probability distribution on the coordinates. So if I think of my high dimensional vector as a probability distribution, so I want to think about my bag of words representation, is if I pick a random word from the document, what's the probability that word's going to be apple? Then I should L1 normalize all my coordinates. They're all going to be positive, and I you know, this is the L1 normalization. There are other ways that work on probability distribution. There's the Hellinger distance and some other ones I won't cover. This is probably the most common. This is the Kell divergence, but this one is not symmetric. But this has something to do with if I know information, if I know the information at A as a information theoretic sort of thing, how many bits of information do I need to send to recover across a channel to recover B? It's effectively measuring this. And so it's a very kind of, it's derived from information theory. We'll actually see this, something like this come up when we talk about differential privacy later on in the semester, but it's not symmetric, right? It's not a metric either. It doesn't satisfy the triangle inequality either. But this is kind of like one of the right things to do in this space. Okay, there are other versions with work on probability distributions, but I think it's interesting just to think about taking your vector and turning it to a probability distribution. In fact, the Kell divergence only works if you don't allow zeros, so you have to add a very small term to all the coordinates if you want to use this for bag of words, which is weird, but it turns out that's kind of the right thing to do still. That kind of is like a regularization term, which again we'll see later in the semester. Okay, so distances are vast and wild and cool, and it's a modeling choice which ones you use. We'll continue to see properties of them, you know, throughout the semester.